Hi guys, assalamu alaikum. I hope you're all well and having a good day. So today we will discuss the most difficult 15 physics unit for multiple choice questions. Hopefully you guys will love this video and please don't forget to subscribe and best of luck for your examination. Alright guys, so our first question is the question number 9 from the year January 2020, which is a difficult question regarding vectors, and this type of questions are really common in our exams, and these type of questions are a bit difficult, so let's solve it right now. They have written the diagram shows the momentum P and Q of two bodies about to collide. Okay, so they are going to collide, and when the bodies collide they merge and move on as a single body. They have asked us to diagram show the resultant momentum, so they have asked us to draw a resultant momentum. So basically the net momentum is not zero, there is a resultant momentum. There is a resultant momentum. They didn't say that the momentum is zero. That means this vector diagram which we will draw will not be in equilibrium. Our diagram will not be in equilibrium. So when something is not in equilibrium, it cannot be a tip to tail diagram. So our diagram cannot be a tip to tail diagram. Our diagram cannot be a tip to tail diagram. This is the things that we have learned. If you haven't yet learned about vector diagrams, then please go through my YouTube channel and please scroll down or search exam essentials vector diagram inclined slope. Then you guys will understand vector diagrams to a very much detailed way. I will drop that video in the description box, and if I don't, then please search it down by yourself. So basically what we'll draw is we will not use tip to tail right now. The diagram will not be a tip to tail diagram. So first of all we'll draw the P1. This is our P1. With the tip of this is our tip, we will draw the tail of the Q. The PQ will be in tip to tail. You might ask me a question that you said that it will not be a tip to tail diagram, but yeah, the P and Q will be a tip to tail diagram. The tip of this P is with the tail of this Q, but our resultant momentum will not be a tip to tail diagram. Our resultant momentum will not be a tip to tail diagram. So this value will be, our resultant momentum will be like this. So you can see here that the tip of this resultant is with the tip of this Q, and the tail of this R which is with the tail of P. So overall it is not a tip to tail diagram, but P and Q is a tip to tail. Overall the diagram is not tip to tail. So let's go through. So we can basically see that this is our correct answer. Our correct answer will be C. All the other ones are wrong. The SI unit of capacitance is the farad. Okay, which of the following gives the base units of the farad? So basically they're asking about the base units of capacitance. We know charge is equals to capacitance into voltage, and capacitance is equals to charge divided by voltage. Okay, so the base unit, the SI unit of capacitance is farad, which can be written as F. F is equals to charge. The SI unit of charge is Coulomb, and V minus. Okay, we have written it like this. Now we know work done is equals to charge into voltage, and if we convert voltage equals to joule C minus 1, because work done divided by charge means work done is in joule and the charge is in coulomb. So when the charge goes up, it becomes JC minus 1. So we can also write it down like that, C into JC minus 1 into this minus 1. So basically what becomes is this becomes J minus 1 and this becomes C into C is equals to. Alright, this is also a multiplication sign. Now this C and this C becomes C squared into this J. Now we know work done is equals to force into distance. Work done is equals to force into distance, and we know if j minus 1, then it becomes nm. Work done is force into distance means Newton into meter will become also minus 1. I have written minus 1 here because it is j minus 1 right here, that's why. Okay, so this becomes n minus 1. So we can write it down as n m minus 1 right here in the place of j minus 1. So now what we can do again is, we know charge is equals to current into time, which can be written as Coulomb is equals to ampere into second in their SI units. Okay, we know F is equals to mass into acceleration, and it can be written as Newton is equals to kilogram ms minus 2. Okay, very good. Now this C can be written right here as a squared s squared, because this a and s both will be squared because here C has c squared. Okay, the next part will be, this Newton will become kilogram minus 1 ms m minus 1 s squared into these m minus 1. So overall our answer will be this s squared and this s squared becomes s4. So we can say it is a squared s4 kg minus 1 m minus 1 into m minus 1 becomes m minus 2. So here it is m minus 2. So yes, this is our correct answer. Our correct answer is C. Point charges of plus q and minus q are placed at x and y respectively. So positive charge and negative charge are placed at x and y. When another charge is placed at z, the resultant force on the x is 0. Okay, so basically the thing that is happening is, there is a positively charged q and a negatively charged q on y and x respectively. Okay, so when they are, so one is positive and the other one is negative, so there is an attractive force. So on x there is an attractive force in this direction from y or minus q. But when another charge is placed at z, the resultant force on this x became 0. So we can say, if the resultant force on x has to become 0, there must be a force that should be acting in this direction, right? There must be a force acting in this direction. If we name this force as F1 and this force as F2, we can say F1 is equals to F2. We write F1 is equals to F2. As the resultant force is 0, we can say F1 is equals to F2. Okay, so for F1 we can say this F2 is the force that this Z has exerted. Just because of that, the resultant force on X become 0. Otherwise it would have never become. Another charge is placed at Z. So when another charge, let's say Q, was placed at Z, that Q exerted F2 force on X, which made the resultant force to become 0, and this force was exerted in the opposite direction to where F1 was exerting. So we can say F1 is equals to F2. So for force we can use the formula of electric field, K into, for F1 this theta and this theta are the thetas on which this F1 force is acting. So we can say K into theta divided by r squared. We don't need to write the negative theta because it's a numerical value, and we don't need to denote the negative or positive charge right here, is equals to this F2. So for this F2, this Q is acting on this Q and this Q. Sorry, my bad. This Q is acting on this and this Q. So we can write K into Q into this bigger Q divided by the whole distance. They have said xy is equals to yz. So if we say this is r like this, then it will become 2r. So it is 2r squared. So now we can write kq divided by 4r squared is equals to r squared k into q into q. Now if we remove this k, these r squared, this q and this q, we will be left with q is equals to charge divided by 4. So this charge, that means this charge is equals to 4q. So our correct answer will be this D. Alright, so let's go through this question. They have written an uncharged capacitor, a resistor, a switch, and a cell are connected in series as shown. Okay, this is a very important concept. Charge, resistor, switch, and a cell. Okay, which of the following shows how the charge stored on the capacitor and the potential difference across the resistor? This is very important. PD across the resistor, not across the capacitor. It's in the resistor part. Vary when the switch is closed. So we all know that when something is uncharged, it will get charged. That means the charge stored on the capacitor will increase. The charge will increase. The charge will increase, not decrease. It is previously uncharged. So when you will connect, or when the switch is closed, the charge will start to increase. The charge will start to increase. So basically, in the points that they have given us, the first point, it is not our answer because here the charge is not increasing. So this cannot be our answer. This cannot be our answer. B cannot be our answer as well. So here, as the charge will increase, A cannot be our answer and B cannot be our answer. We will cross them out because here the charge is decreasing, but it is an uncharged capacitor, and when we will close the switch, the charge will start to increase. So you cannot answer A and B. Now here comes the PD across the resistor. So our answer will be anyone between C and D because here the charge is increasing. Now they have said the potential difference across the resistor. How will that potential difference across the resistor vary? We know the potential difference across the resistor when the switch was opened was equal to the EMF. We know EMF is equals to VR plus VC. Here at the start VC was 0 and VR was equal to EMF or maximum potential. But as the switch is closed, the voltage across the capacitor will increase and the voltage across the resistor will decrease. So we can say our correct answer is C because here the charge is increasing as it was uncharged before, and the potential difference across the resistor decreases. So it's very important to read the resistor part because otherwise the student would have written easily given the answer as D. But no, the answer is not D. The answer is C because it is talking about the resistor. A positron and a muon travel at the same speed through a magnetic field. Okay, so their speed is similar. Alright. The magnetic field is directed into the page. The magnetic field is directed into the page. Which of the following best represents the motion of the particle? Okay, the motion of the particle. Now, as the magnetic field is directed into the page, okay, as the magnetic field is directed into the page, if you put your first finger into the page and your second finger upward, you can see that the force is on the left. So as the force is on the left and positron is a positively charged particle, so its force will be in the same direction as the motion. So we can say our answer is between C or D. So now we have to find out another thing. We know muon has a greater mass than positron. Muon has a lot more mass than positron, and they have the same speed as well. So basically muon will have a greater momentum. According to momentum is equals to bqr. Okay, as it has greater momentum, it will have a greater radius as well. It will have a greater radius. So we can say in this part the muon has a greater radius than the positron. So our answer is basically answer C. Alright, so now moving on to this question, they have written a wire is held firmly in place between two magnets mounted on top of an electric balance. The reading on the balance is 1.500 Newton. Okay, the magnetic flux density has been given and the wire is connected to a circuit, so there is a current in the wire. So in this wire a current will flow and the reading on the balance is 1503. Okay, so basically what they have said is when the current has started to flow, the balance on the scale has increased. The balance on the scale has increased. So one very cheat note that I want to say to all of you guys is, just before the exam, I don't want to make these things difficult. In this type of scenario, a student starts feeling that as the balance has increased, there must be a downward force acting which has increased. So they might think that the force on the wire is acting downward, that is why the balance has increased, the magnitude of balance has increased. But no, this balance always shows the normal reaction force, not the weight. This balance always shows the normal reaction force. So as the value of this balance has increased, we can say that the value of normal reaction force has increased. So normal reaction force is a force upward. So as these values increased, we can say our normal reaction force is increased. So as the normal reaction force is increased, we can say the force on the wire is upward. The force on the wire is upward, we can say that thing. Okay, now what they have saying is, which of the following gives the current in the wire and its direction? So we have to first figure out the direction of the current. We know the force is upward. The force is upward. Okay, very good. The force is upward. The magnetic field is into the paper because it's north and south. It's the north and it's south. If you put your thumb in the upward position, your first finger into the paper, you will see that the magnetic field is from X to Y. The magnetic field is going to the right. So we can say our answer is either this one or this one. Now we have to figure out this math. In order to use current, we have to use the formula of force, because here the force is acting. So the only formula in magnetic field is F is equals to BIL. Now we need to make current the subject, current F divided by BL. So here our force is 0.003 divided by B, which is 0.07, into the length. The length is 5 centimeter. They have given it right here, which can be written as 0.05. So basically our answer will be A, not C, because here the values are wrong. So we are done with this question number 8 as well. So basically in this question, the diagram shows how the track of a charged particle in a magnetic field. So here the magnetic field is directed into the page. Okay, very good. This is an important part. Now, which of the particle could create this track? This is the question. Now you can see when a particle is moving in a track, it loses its energy. So when it loses its energy, its radius of curvature decreases. So here in this part, the radius of curvature is less, and here the radius is greater. So we can say the particle is moving from Y to X. That's why as it is moving, its radius of curvature is decreasing. So we can basically say that our answer will be from Y to X. So here we can cancel out these two. Now the answer will be between them. Now we know the force is always perpendicular to the direction of motion in a magnetic field. The force is always perpendicular. So let's say the force is in this direction. Now as the force is in this direction, okay, as the force is in this direction, or we can say like this, that here the force is in this direction, the force is upward. We know when the force is upward, the current is in this direction and the magnetic field is in this direction, if you use the Fleming's left hand rule. This is our force, this is B, and this is our I. So our force is always perpendicular to the direction of motion. Here the force is upward. If the force is upward, because it is always perpendicular to the direction of motion, as it is moving here, the force is upward. Okay, the force is upward. Now they have said the magnetic field is directed into the page. So we can say, let's say, let me draw it up in a much better way. Actually, it is not that clear right now. Yes, now we can say this is the direction of motion. So our force is perpendicular to it. The force is perpendicular to the direction of motion. Okay, the force is perpendicular to the current. As the force is in this direction, the magnetic field is into the paper. We can say the magnetic field is into the paper. So if the magnetic field is into the paper, if you use Fleming's left hand rule, you will figure out that current will be in this direction. If you use the Fleming's left hand rule, if the force is upward and the magnetic field is directed to the page, you can see the current is in the right direction, but it is moving from Y to X, so it is moving in the opposite direction to the current's direction. So it is a negatively charged particle. Here an electron is a negatively charged particle between positron and electron, so our answer will be D. Fleming's left hand rule is really important in this part, and one part you need to understand is the force part. That force is always perpendicular to the direction of motion. Here the force will be here like this, because the force is always perpendicular to the direction of motion. This is the direction of motion, right? And the force is always perpendicular. The force is always perpendicular to the direction of motion. Current is the direction of motion. Delving into the question number 9, a ball traveling at speed u towards a collides with the wall at right angle. So it is colliding with a wall. So let's say this is a wall and a ball will travel in this direction and collide with it. Okay, very good. The ball bounces off the ball at speed in opposite directions. The ball will also bounce off like this. The time for the collision is t. Which of the collision gives us the average force on the wall during the collision? Okay, so the force on the wall, we know during this type of things, the only formula here you can see mv by t. So basically it is the second law formula. F is equals to rate of change of momentum. So F is equals to mv minus mu divided by time taken. This is our formula, right? Here let's say in this direction the ball is moving in this direction. Let's say this is our positive, and here as the ball is moving in the right hand direction, let's take it as negative. So the initial velocity will be positive and the initial velocity and the final velocity will be negative. So we can write it down like this, that minus mv minus mu divided by time taken. This mu is positive and this mv is negative, and there is negative value like right here. So this is actually the value that we have figured out. Now as it is minus mv minus mu divided by time taken, let's convert them into positive ones. Let's write it down as mv plus mu divided by time taken, and you can also write it down as mv plus u divided by time taken. So basically our answer will be this. No, basically my bad, the answer will be A. So our answer will be A. We cannot take 2t, we will take 1t, because the time they have set for the collision, so the overall collision. So our answer is A. We don't need to add 2t because the time here is for the whole collision. We don't need to take about, they didn't say that for the collision in this part and in this part. If it was like that, then we would have taken 2t, but they have said for the whole collision, time for the collision, that means the whole the collision, not for the positive towards the positive or negative, not that. They have said time for the collision, that means it is for total time. So t is our total time, not 2t. So our answer will be A. Alright, so a car travel over a humpback bridge as shown. The bridge forms part of a circle of radius r. So let's draw it like a circle here. We can say that the car is traveling over a circle. So this is the circle on which the car is traveling. Let me draw it in a much better way. Okay, so the car is traveling over a circle with constant speed and mass m, and the radius is given. Okay, a circle is at the top of the bridge. Which of the following expression gives the force from the bridge on the moving car. So they are asking about the force on the bridge from the moving car. So let's draw a circle right here. So force from the bridge is the normal reaction force, right? The force from the bridge is normal reaction force. Here the car is in contact with the bridge. The car is in contact with the bridge. So let's draw the forces that are acting on the car. The first force that is acting on the car is its weight and its normal reaction force. So they have asked us to figure out the force from the bridge. Normal reaction force is the force from the bridge, right, on the moving car. So they have asked us to figure out this. Now as it is moving through a circular radius, there will be a centripetal force. So we know the centripetal force is the force that is acting towards the circle, right? That is acting towards the circle. There are two forces. We know centripetal force is the resultant force of the forces that are acting towards the circle. Okay, so there is two force. We can say that centripetal force will be between the resultant of these two forces. The centripetal force is the resultant of these two forces which are acting towards the center of the circle. We can say mg minus r is equals to our centripetal force, which can be said as mv square by r. So they have asked us to figure out the r. So our r will be mv squared plus mg. So our correct answer will be B. We are done with it. Alright, the solid line shows the path of an alpha particle as it passes close to a gold nucleus. So basically this is the path of the alpha particle. A second alpha particle with the same kinetic energy, this is important, approaches the gold nucleus. Which dotted line shows a possible path for the second alpha particle? So here we can see this was the first alpha particle which was deflected by the gold nucleus. Okay, so they have asked whether this or this, which is the second, which can be the second alpha particle with the same kinetic energy. If we look at the part A, we have seen in this first alpha particle that it was deflected away, it was repelled, it was moving away from the gold nucleus. But here A is coming towards the gold nucleus, so it is having an attractive force. It cannot be our answer because the same alpha particle will have a repulsion force, because the first one was repelled by the gold nucleus, but A is coming towards the gold nucleus, so it is attracting. So A cannot be our answer. Now moving forward to the B, we can see B is more closer to the gold nucleus than this first alpha particle, so there must be a greater force acting on it. We know F is equals to k theta 1 theta 2 divided by r square. As the radius decreases, the force increases. So B has a lesser radius than the first alpha particle, so the force must act greater on B. So this B should have deflected more because the greater force was acting on B. As it has deflected less, B cannot be our answer as well. Now moving forward to the D part, D is moving in this direction, so it would have been deflected like this. It should have been deflected like this from the gold nucleus. So it is moving in this direction, that means it is attracting. So D cannot be our answer as well. Now C is the perfect answer because it is going in this direction and it was deflected, and it has a greater deflection because it was closer to the gold nucleus. So our correct answer is C. The other ones are not the correct answer. Okay, in the question number 7, they have said a square coil PQRS has a side length of L. There is a clockwise current in the coil as shown. The plane of the coil is parallel. This is very important. The plane of the coil is parallel to the magnetic field of magnetic flux density D dash. Okay, so as it is a clockwise current is going, if in this direction it is upward, then in this direction it will be downward, like this, right? The coil is in the clockwise direction. Okay, very good. Now they have said the plane of coil is parallel. So as the plane of the coil is parallel, there will be zero magnetic force right here and right here because they are parallel. We know for the magnetic force to act, the coil or the plane of coil or the current needs to be perpendicular to the magnetic field. The current needs to be perpendicular to the magnetic field. Right here the current is parallel, or the plane of the coil is parallel, so there is no you cannot use the Fleming's left hand rule and there is no magnetic force. So here in the PQ part the magnetic force will be 0. So basically our answer will be A. Now you guys might have a question, why didn't I answer the other ones? So let's talk about this part. Here the current is upward. Here the current is upward. If the current is upward, if the current is upward, and the magnetic field is into the right. Magnetic field is into the right. The force is into the page right here. The force will be into the page right here. So here you can denote it as X, and here the force will be out of the page because the magnetic field is into the right, the current is downward, but the current will be out of the page right here, and the current will be into the page right here. These are the things these are the basic things which you guys need to know. So here if you look at QR, it is current out of the page, but they have written magnetic force 0, so it cannot be our answer. They are talking about RS. In the RS portion, the magnetic force is 0 because it is parallel to the magnetic field, so it cannot be our answer. Now talking about SP. So SP, in the SP part, it is magnetic field into the page, but they have written out of the page, so this is not the correct answer as well. Or basically the correct answer is only this A. So we are done with this. Okay, so in the question number 4, they have said the diagram shows the shape of the electric field pattern between two charged particles X and Y. X has a charge of minus Q. So they have asked what is the charge of Y. Now here we can see that both the electric fields of X and Y has diverged. They have moved in these directions. They have diverged. Okay, so by saying diverge, I'm meaning that when both of them have moved down, none of them have moved in this direction or in this direction from X and Y. They have actually diverged. They have moved away. So that means here is a neutral point right here. Here is a neutral point. So for a neutral point, both of them needs to be a negatively charged particle, or they have to be the same charges. They needs to be same charges. As X is minus Q, then Y will also be a minus charged particle, because for both of them to diverge or to move away from each other and not colliding or not moving in the same direction is because they are of the same charge. They are repelling each other. As they are repelling each other, they are moving away. But here you can see for X, the density of the electric field lines are lesser. The density is lesser than the density here. The density in the Y part is greater. So as the density is greater, it will have a greater charge. So here, as it has minus Q, it will be minus 2Q. So our answer will be B. Now I want to make you guys understand one particular thing. The thing is, this is called neutral point. When both of them has the same charges in this point, it is called a neutral point. In the neutral point, if you put a particle right here, it won't experience any electric force, because both of the particles X and Y, because both of the charged particles X and Y are of the same charge. That's why the electric fields are moving away from each other. They are repelling from each other, and the charge of Y is greater than the charge of X because it has greater density of electric field lines. Now if I make you guys understand in a very simple way, my explanation will be the field lines in the diagram diverge, means they are moving away from each other or they are repelling each other, showing X and Y are like charges, both are negative. The equilibrium point or the neutral point is closer to X, meaning Y has a greater magnitude of charge. Since X is equals to minus Q, Y must be minus 2Q to satisfy both the divergence of field lines and the location of the equilibrium point. Therefore, our correct answer will be B. The main reason behind it having a greater magnitude of charge is because it has greater density of field lines. Now we are done with the question number 4 as well.